큐스타 팀에서 처음으로 발표를 하실 텐데, 이제 첫 번째 발표자가 어떤 분이시죠?
네, 접니다.
아, 네. 그럼 발표 자료 공유 먼저 부탁드리고요.
네.
네. 그러면 이제 오늘 리서치 멘토링 프로그램 최종 발표 시작하도록 하겠습니다. 오늘 두 번째 날이고요. 오늘은 총 다섯 팀이 예정이 돼 있었는데, 이제 마지막 팀이 이제 사정상 참석을 못하게 돼서 유튜브 비디오로 나중에 녹화 발표자를 공유를 하기로 하였습니다. 그래서 오늘은 총 네 팀이 발표를 할 계획입니다. 첫 번째 팀은 Qstar 팀이고요. Curriculum Reinforcements Running QAS and its use for unitary synthesis에 대해서 발표를 해주시도록 하겠습니다. 네.
Hello, everyone. Today I'll be presenting our work on using curriculum reinforcement learning for quantum architecture search and its extension to unitary synthesis. This is a joint work between Qstar members, myself, Hyunho Cha, Minjin Kim, and of course our mentor, Willie Aboumrad, and help from San Kim. We'll begin by introducing QAS and curriculum learning. Then we'll explain the Stargate-based optimizer, followed by the core goals of our work and the current progress, including results. The variational quantum eigensolver, or VQE, is a hybrid quantum classical algorithm used to estimate the ground state energy of a Hamiltonian. It's one of the most promising algorithms for near-term quantum devices. The classical optimizer updates the parameters based on the quantum measurements, aiming to minimize the system's energy. But here's the catch. The performance of the VQE heavily depends on the quality of the ansatz, the quantum circuit structure. If the circuit is too shallow, then you can't express the ground state. Too deep, then noise kills your signal. So designing a good circuit architecture is critical. That's why people came up with QAS. QAS stands for Quantum Architecture Search. This automates the process of finding a suitable circuit architecture. Instead of guessing the ansatz, we let an agent learn to design it. A notable work using Curriculum RL-based QAS was recently published at ICLR 2024. In the matter of building a quantum circuit, this can be applied to unitary synthesis. This tech requires building circuits that match a target unitary, a key component of quantum compiling and circuit optimization. Before we get into, it's worth taking a step back and asking, why is this problem important? First, it plays a vital role in quantum compilation. Any abstract algorithm must eventually be broken down into gate-level operations that run on hardware. Second, in algorithms like VQE or quantum phase estimation, we often need custom unitary blocks. These aren't always standard gates, so synthesizing them from primitives is crucial. Now, here's the implementation of CRL-QAS. The agent incrementally learns to build deeper and more complex quantum circuits as its performance improves. You can see that based on the current state, which is the structured circuit, the agent decides what gates to choose next. In this figure, the agent added the RY gate, which is the rotation of the y-axis, in the end. Then the classical optimizer will calculate the lowest energy and give the reward to the agent. Then how would the reward look like? It is built with the cost function, which is the error between the target energy and the current energy. So if the agent reached the threshold value and gets an error smaller than that, we give a strong reward of +5. If it reached the maximum number of steps in iteration and still couldn't get to the threshold error, we give a strong negative error of -5. Otherwise, if the error got smaller than before, we give a weak positive reward. And if not, we give a weak negative reward. Curriculum learning trains models from easy to hard tasks, mimicking human education. It's been effective across various domains and we apply it to quantum circuit design. Here, we adopt a feedback-driven approach where test difficulty increases based on the model's performance, ensuring a smoother learning curve. Specifically, the target energy will get lower as the episode continues. The agent aboves redundant gate sequences to make the search space more efficient and prevent wasting learning on invalid actions. For example, two CNOT gates will not be added together, since they would remove each other. Also, same rotation gates will not be added together because they will act exactly the same. Furthermore, if the parameter angle of a rotation gate is 0, it means that the gate is useless, and it means an identity matrix. So we give a strong negative reward for that too. This shows the matrix form of gate selection and placement. Each position represents a gate type at a specific qubit and depth. For example, let's look at the first depth gates. The row of the matrix means what kind of gate it is. We use the C naught and rotation XYZ here. The column of the matrix means the qubit to work on. Especially for C naught gates, the column means the control qubit, and the row means the target qubit. So if the row is higher than the number of qubits, we automatically know that it is a rotation gate. Let's recall the CRL QAS agent again. The original hybrid quantum classical environment need to use classical optimizers like Adam SPSA and Cobila to get the lowest energy and optimized parameters. This requires lots of computing power and energy because we need the energy function for each ansatz and optimize it for numerous iterations. However, we replace the classical optimizer with a surrogate-based optimizer. Instead of calculating the energy Hamiltonian back in the classical computer, we fit a model to estimate the energy and guide the search. Our environment tests circuit quality efficiently, requiring minimum quantum measurements. This is key to scaling. The SPO method measures few number of shots, around 20, randomly in a bounded parameter space. And then it uses the Gaussian kernel to find the location of the lowest energy. Next, the parameter sampling space moves closer to the minimum and repeats until it meets the local or global minimum. The black square in the figure is the selection of samples, and the red square is the boundary that the center of the space can transfer. Our goals are threefold. First, improve the SPO, enhance the CRL-QES agent, and explore new directions and like unitary synthesis and classical shadows. First, we test how changing the SPO's internal parameters, such as batch size L, affects convergence. L is the size of the black square in this figure. The basic idea comes from the right figure. The SPO uses a fixed size of sampling space. However, it looks like that if the sampling space increases by the energy difference, we can reduce the number of iterations and converge faster. This is the result of the experiment. You can see that the SPO with changed L is better at figuring out the lowest energy of the problem. This experiment shows that tuning the model can enhance optimization. We also improved the QAS agent, especially by adding SPO operate directly. This uses the quantum optimization and requires fewer shot numbers of 20 for each handsets. Here's the result of combining CRL with SPO. The original QRS works better in shorter steps. However, with only one of fifth number of shots, the SPO succeeds to find out the lowest energy. For last, we apply our approach to unitary synthesis, as mentioned before. To make this work, we redefine the agent's reward using gate fidelity between the constructed circuit and target unitary. This makes learning more directly aligned with synthesis accuracy. The gate fidelity is basically shown like the equation above. There are several gate fidelities, but here we are using the average gate fidelity to explain the gate more generally. This plot shows how curriculum learning helps the agent escape local minima and achieve higher fidelities over training episodes. We present results for 2, 3, and 4 qubit unitaries. From the 2 qubit results, we were able to get the highest fidelity of 0.857 for a random unitary matrix. For the 3 qubit results, we were able to get the highest fidelity of 0.361 for a random one. It finds that 3 qubit problem is still a hard task for the agent due to its large start space and long circuit length. For 4 qubit matrix, the obtained maximum fidelity of it was 0.247. It is shown that it takes much longer steps for the agent to learn from the problem. Beyond 4 qubits, the problem gets more challenging because when we calculate the circuit into a matrix form, which scales as the 2 to the power of n, this quickly becomes infeasible in classical hardware. Therefore, we need to think of a method using the measurement of an actual quantum device. We might need to restrict the unitary matrix too. We explore classical shadow tomography as a scalable alternative. It estimates properties of quantum states without full matrix reconstruction, but estimating a density matrix of the quantum state. It chooses a random basis of a quantum system and measures it. This is the same problem with 4 qubit, but using the shadow tomography. The fidelity result increased up to 0.4. This shows that shadow-based methods maintain reasonable fidelity estimation and synthesis quality when the system size grows. We also test our method on real quantum hardware in IonQ's area QPU. This shows validation of our approach in noisy real-world conditions. Questions still remain, like why simple circuits sometimes fail to converge. This might connect with the barren plateau problem, which mentions that the parameter gradient disappears as the gate length increases. Future work includes speeding up optimization, improving fidelity estimation, and extending to larger systems. This might be done by restricting the unitary matrix with shorter circuits and curriculum learning from shorter circuits to longer ones. These are the key references that influenced our work. Thank you for listening and feel free to ask any questions.
Thanks for your presentation. I have one question. You mentioned like using curriculum learning, you actually avoid the local minima. Could you explain a bit detail? Could you elaborate a bit more how actually you use curriculum learning to actually come out of the local minima?
Sure, that's actually a good question. Um, for the energy estimation, we don't know the bound energy because that's the goal of the project, like measuring the lowest energy of the Hamiltonian. So we start with uh, a minima that we choose. We choose the a randomly lowest energy as a goal, and if we um, learn the agent and actually get uh, we into that goal. So if we go under this threshold of epsilon two, uh, uh, no, sorry, I'll do it again. If we go under the first threshold energy of epsilon one, then the agent lowers the threshold energy to epsilon two. So that's the going to the harder problem. So because the lower energy is much harder to get. And if we get stuck at the target energy of epsilon 2, it means that we are stuck in the local minima. So we just change the threshold energy and make it into a little bit easier one by adding the delta. So we force the energy back and start learning again, and then we'll try to get under the threshold value of epsilon 2. And if it gets stuck every time, it means it's almost the lowest energy. So that's how they use curriculum learning in this um, paper.
Okay, thanks for explanation. Do you see some like benefit of speed up compared to like training from like some section of like the parameter space, which is basically like it seems to me like you are lowering or you are hiring the bars of the threshold so that actually you are kind of like traveling over the optimizing landscape. So is it like actually providing us like a benefit in terms of time to actually come out of the local minimum, or it would be better off like we start like from like some vast candidates and kind of screening out for better optimization. Does it make sense to you?
So I think basic idea of using this curriculum learning method is that you need a good reward function for the agent. So um, if we don't have uh, the goal energy, then the agent would not be able to get a fine reward, and it wouldn't know where to go, like which energy is the better option. So that's the first reason why uh, we are changing the threshold value. But in case of changing the difficulty, somewhat kind of parameter values, as you said, we can use that into the change of the circuit depth in my problem. So in my problem, I went to the problem of reaching the higher fidelity as highest as one. But um, in this version, we have different circuit length. So when the circuit length gets higher and higher, it means it's a harder problem for the agent. So I'm looking forward for future work to change the difficulty as the circuit length and increasing the length by one and one, and finally reaching for any arbitrary gate lengths.
Okay. Thank you. Thank you for your answer. Great presentation.
Thank you so much. Yes, please.
Yeah, thank you for the presentation. I have two questions. One is there is work on using machine learning to learn gate decompositions of gates. For instance, the Toffoli gate. It's a famous 3-qubit gate. Have you applied your method to the Toffoli gate or other
Uh,
specific gates that exist on, say, 3 or 4 qubits? That's my first question.
okay, I'll answer to the first question first. Um, there are several selections to choose the basic gate sets. So in my research, I use the CNOT and rotation gates, right? And most of the RL agents do not choose the 3-qubit gates, because if we have n qubits, then there are selections of n combination 3 of the selection of the gate. So it it increases the search space too much. So um, we didn't use the 3-qubit gates in this paper, but um, I believe that there are some research using decomposing the larger qubit gates, but they can be also represented to a unitary matrix, right? So
Yes.
So that I think if we get the input of the Toffoli gate as a unitary matrix, and we can get the almost same result.
Oh, that will be interesting to see because these papers that I've seen, they get to like 99.9% worst case fidelity by learning the angles also over like C naught and local gates. It would be interesting to compare your approach to those approaches. The other question I had was, um, how robust is your approach against decorating the target gate with local gates? So you have your target gate, but now instead of this gate, you would kind of do single qubit rotations before and after, which hopefully would not change the fidelity much. Have you tried experiments like this?
Can you explain the adding the gates on the side again?
So if you had a gate that you want to decompose, you apply your method, you find the decomposition. So instead of this gate, you would do kind of, you change it variationally by doing single qubit rotations that are parametric. Do it before and after. That should not change the circuit complexity much, but your method might benefit from it because it might kick you out of a local minimum.
Mm. Yeah,
Have you
that's
thought
true.
about it?
Um, but I think the problem is slightly different because if we have already a target circuit component, your method might work. But this problem is considering a problem that we don't have the target circuit. We only have it as a matrix representation.
Mhm.
Uh, so it doesn't, if we consider that if we already have a target matrix, it's something like the circuit optimization, and that it's slightly different with circuit unitary synthesis.
Interesting. Okay. Thank you for the answer.
Thank you so much. Are there any other questions? Okay, I think it's up for me. Thank you for listening, and thank you for this research program. Oh, okay. Thank you so much.
Junkie, are you here? I think not. So I'll go ahead and introduce the second team. The second team is called Quantum Collider, and they were also mentored by Willie. And their presentation topic is QITE for HEP combinatorial optimization. Are you ready?
Yes, I will make the presentation. Okay, just wait. So, okay, let me start. So, thank you very much for the introduction. My name is Hichani in Quantum Collider team. I will be presenting what we learned for past few weeks. Before beginning, we would like to thank IonQ and Willie for providing the great opportunity. We really appreciate our mentor Willie for his time and all the advice every week. Thank you, Willie. We worked on the variational quantum imaginary time evolution for the combinatorial problem in high energy physics. So in high energy physics, we want to understand what happened when the universe was created, what the fundamental building blocks of our universe is, and how they interact with each other. To achieve this goal, we used the Large Hadron Collider located in Geneva, Switzerland. The LHC allows us to explore the universe down to scale as small as 10 to the minus 20 meters in size and as early as 10 to the minus 12 seconds after the Big Bang. With this large particle accelerator, we collide two batches of protons at total energy nearly 14 teraelectric volt, which is the largest energy that humans have ever created in the laboratory setting. The collisions of protons produce many particles from a few to tens of thousands. By studying the properties of the produced particles, we aim to understand what might have been happening in the beginning of our universe. Some of these particles originated from the common source, but experimentally, we cannot always determine which particles came from which specific process. This is the challenge. This challenge is known as the combinatorial problem in high-energy physics experiments. So here is the cartoon version of particle collision and production. As shown in the left diagram, two protons create n number of particles. Some are correlated as indicated in blue or red in the middle plot. Our goal is to partition n particles into two particle groups, A and B, as shown in the right diagram, and compute the energy momentum of the two particles A and B. We consider the two protons creating two mother particles, which then decay into n particles. This is because this is the simplest possible setup and in fact quite general. To set up our problem more quantitatively, we introduce a binary variable xi for each particle I, whose momentum is pi. We assign 1 to the binary variable if the particle I belongs to A, and the other hand, we assign 0 if the particle I belongs to B. So then the momentum of particle group A and B can be written as in these capital P1 and P2. Then we plug P1 and P2 into the Hamiltonian and obtain the following expression, which is similar to the well-known Ising model. Here, x-binary variables take either 0 or 1, but with simple modification, we get s spin variables that we could replace the value in either 1 or -1. Simple physics discussion motivates the use of the energy difference as the cost function of Hamiltonian, which is h0 here. Another possible answer is for the Hamiltonian is p1 square plus p2 square, which is expected to be small when particles A and B moves very fast. So we define our problem Hamiltonian as the linear combination of two H0 and H1 with one hyperparameter lambda. Lambda matches the dimension of the Hamiltonian and makes not to be dominated to the total energy. This simple computation shows that our combinatorial problem at the LHC experiments becomes a cubic problem. So we took, during the program, we took production of quark as an example. This results in 6 particles in the final state. The combinatorial for this example can be regarded as a max-cut problem with a fully connected hexagon, and the coefficients are not constant. It depends on each particle's momentum. A previous study of the problem used quantum algorithms such as QAOA and Falcon. The plot shows how efficient each algorithm resolves the combinatorial problem. The x-axis is related to the speed of the quark model particles here. It is easier to classify higher speed range since the structure of the particle separation is more distinguishable and they tend to be more collimated. So then QAOA give a better results than the hemisphere analysis, which is a classical analysis method, but QAOA is a hybrid algorithm which uses a classical optimizer, and there is some issues to simulate if we use higher order terms for the Hamiltonian. Falcon shows a good performance for the problem, but it needs a large number of gates, which is unrealistic to implement nowadays. So it is important to investigate an alternative method to resolve the combinatorial problem, and we decide to use kite for this problem, since kite doesn't struggle with the mentioned problems here. So during the program, we want to understand the basic idea of what where kite is, and we aim to implement it with paneling to apply the problem at the LHC. Also, we want to think another Hamiltonian ansatz that includes higher order terms and see the efficiency. Finally, if it is possible, we want to run the developed codes on the real hardware. So for a brief explanation of Verkite, Verkite is an algorithm deriving from quantum time evolution that quantum state evolves in the imaginary time. For a time-independent Hamiltonian, a given state can be expressed with the energy eigenstate. As the state evolves in the imaginary time, the probability of the energy's eigenstates decays related to their energy. Finally, the state will converge to the ground state. That's the key point, what we want to the Verkite does. So using this principle, the time evolution is replaced to updating the parameters for a quantum circuit ansatz. So Verkite uses Maclaurin variational principle in updating the parameters. This minimizes the energy difference between the right-hand side and the left-hand side of the underlined equation, which is the Schrödinger equation in imaginary time. It could be thought as solving the linear system of equations shown in the left box here. There was a paper using kite to solve the combinatorial problem from IonQ. As we use Pauli terms for the problem Hamiltonian, IonQ researchers suggested some simplification of the calculation. We can simplify the linear equation like the right box. It makes it easier to implement and reduce the computation cost. After that, we can solve the derivative of the parameters, and for each time step, we can update the parameters with some learning rate. As our Hamiltonian is the well-known Ising model, we will measure the Z eigenvalues of the final circuit result. And to use Verkite, we design a variational circuit ansatz, which is the initial preparation to run the algorithm. We first used the fully connected ansatz, which is suggested in the IonQ paper, but it was hard to get a good performance from this ansatz. So we designed a new ansatz involving assumptions that there will be 3 particles in each group. It is implemented with the decay state, operations with reconfigure beam splitter gates. The RBS gates makes the operation to the amplitude for the given initial state. It makes constraint in manipulating the amplitude within the initial state. So then here's the result. We check the problem Hamiltonian first, which is H0 plus lambda H1. The left plot shows the results of the problem Hamiltonian of the H0 plus lambda H1. The right plot shows the result of the H0 Hamiltonian. Comparing to the previous results, kite methods gives better results than QAOA, but not as efficient as Falcon. Here, the blue straight line is the Hamiltonian limit resolving the problem, and the black lines are the results from kite. The dotted is from the fully connected ansatz, and the straight line is the ansatz with assumption. The color line with yellow, orange, and red are the previous quantum algorithm results. Generally, the ansatz with assumptions gives an improvement than without any assumptions. As we handle a symmetric problem that T and T bar has the same energy, the performance of H0 is better than the H0 plus lambda H1 Hamiltonian. That's why the right plot shows some better results here. Then also during the program here, we try a new Hamiltonian candidate that includes the quartic term, just a simple multiplication of H0 and H1. The Hamiltonian was more efficient in slow speed range than H0 plus lambda H1. And in high speed range, it is somewhere between H0 and H0 plus lambda H1. But the results from chi seems not so efficient than the previous Hamiltonian results. We think there was not sufficient steps to check convergence to the ground energy. ground energy. So we have done almost the things we planned, except running the developed codes on real hardware. We understand the basic idea of where kite. We implement the algorithm and apply to the simple problem at LRC. And also we try different Hamiltonian ansatz, which includes a quartic term. There was some trial to run in IonQ QPU, but there was no sufficient budget to use and see any results. So for a summary, we learned that VerKite gives better results than QAOA for solving our problem. We could get some freedom to use Hamiltonian with higher order terms, so that it will be a good quantum algorithm candidate for solving the combinatorial problem at average C. And for further away, we could apply some other process examples, such as some process that have more particles and some anti-symmetric energy group. However, it was hard to resolve the problem with non-constant coefficients and also, as we checked the convergence process, there was a problem that Verkite struggles in a local minimum here. So we could consider the followings to improve and develop the Verkite resolving our problem. Designing the ansatz with assumption gives some improvement for our problem, but we don't know specific information of the production of the particles, so we want to avoid such occasions that in real experiment. This will be lead us exploring different ansatz without any assumptions. We can study the impact of the noise for the Verkite method and see whether it is still efficient and how to implement efficiently under the noise. Then, if there are some sufficient budget, we can run Verkite and make some analysis with the real quantum hardware. So thank you. It was Hee-chan Lee. The code and data are available in my GitHub. Thank you. That's my presentation. So any question here?
I have a question. Very nice presentation. First, but could you explain a little bit the intuition that led you to choose that second ansatz as opposed to the first one, the fully connected one? Yes.
Yeah, so for the fully connected one, we do not give any assumptions for the ansatz one that for the initial state, the ansatz one gives all the possibility for the state, right? But for the ansatz two, we choose the decay state first because the example we choose here, the production of T bar process, each T quark and T bar quarks produce three particles here, and it leads. And the initial state is designed with the decay state that the six particles are divided in two groups with three particles here, and the RBS gate operation gives some manipulation for the amplitude that is constrained in the initial state. So that's how we designed the ansatz 2 here.
In the RBS gate operation portion, those are ZZ gates. What are the single qubit gates?
Here it is RY here, but
Okay.
in one box here, like here in the box, the RY has the same parameters here.
Okay. Thank you.
Yeah, any question?
Yeah, a couple of questions. Thank you very much for the presentation. I did not quite understand if you used noises simulators or if you used noiseless simulators. I understood that you did not get a chance to run on quantum hardware,
Yeah.
but did you use noisy simulators?
No, we just run in the ideal simulator and just yeah, that's all. We will try some for the future work. We can try with the noisy smell noise with a simulator with the noise after then. I think.
Okay, not a problem. And then another thing I was wondering about, you mentioned briefly a connection to max cut.
Yeah,
I did not understand though where the graph comes from. It seems like for a fixed number of particles, like
yeah.
on both sides, let's say same, it's always going to be the same graph. Is that correct?
Uh, so can you repeat the question? I mean, I think I could understand what you mean.
So I was curious about what is actually the input to the problem. So
Ah,
what constitutes the input? It seems that the input is just the number of particles that will result in the collision. Is that
yeah.
correct? So you get basically one number, maybe similar to the labs problem, if you're familiar with that. You have
Uh,
only one number that characterizes the entire problem. Is that correct?
maybe so. v- maybe not just the so. I
I
think
think I think the
John, maybe
three
I can jump in
components.
here for a second. So if you go back to the other slide, I think what Martin is asking about is like what's the input data? And part of the input data, Martin, is experimental data about the collision itself. So they have information like these J's. Those are all collected from experiment. They measure the momenta of the particles as they move away from each other upon collision. So all
Oh, okay.
these coefficients are problem data.
Oh, I see. Okay. I thought for some reason they're either there or not there, and it all depends on just the diagram.
Oh,
also
Okay. Thank you. That
well,
clarifies.
actually, it's the PJs to be like very precise. It's the PJs that are the experimental data, and then they compute the rest of the coefficients by these formulas. So these formulas, like the capital P1s, those measure the momenta of each of the particle groups
Okay.
or them.
Let me just add that the input from the experiment and the momentum
You know,
will appear as a weight on the edges. So the graph will look similar, but the weights are different at every time.
Understand. It's a weighted graph. Okay. Perfect. Last question I have. How does the kite method that you implemented compare to QAOA, in particular in the number of parameters? So if you have a comparable QAOA ansatz with comparable performance, did you get to compare the number of parameters in the both cases?
so here the QAOA results have training parameters with 30 parameters. It was 30, yeah, I think I remember that 30 or 16 there. And as our ansatz have only training parameters with 15 number of parameters, so this results here will be comparable to each other, I think.
So 30 for QAOA versus 15 for kite.
Yeah.
Okay. Interesting. And did you map this out, how this would scale for a larger number of n of groups? How would it scale? How many parameters would be needed in your ansatz?
We also doubled the parameters for 30 when we run kite, but there was just a slight improvement, not so much. So maybe 15 will be a proper starting point here. And yeah, that's what we checked also during the programming.
Okay. Well, thank you very much again.
Thank you. Thank you for good questions. Any other questions? Okay, then it's up to me. Thank you, IonQ, and yeah, I will final my presentation.
Thank you very much. That was a very nice presentation. And now we'll shift to a team that was mentored by Sang. The team is QPlayer, and the title of their presentation topic is Optimizing Varkite for Efficient Quantum Simulations.
Okay, can you see the slide well?
Yes.
Okay, let me start. Hello, I'm Youngmin Kim from Team QPlayer, and our mentor is Sean Kim. We are very appreciate Sean Kim for mentoring. I'll present our project optimizing Varkite for efficient quantum simulations. Our project focuses on variational quantum imaginary time evolution, or Varkite. The previous team explained Varkite very well. Varkite is an algorithm designed to solve combinatorial optimization problems by finding the ground state of a Hamiltonian using a parameterized quantum circuit. The parameter updates in Varkite are performed as shown in the equation on the slide. In this project, our goal was to optimize Varkite. In Varkite, the parameter shift rule is used for parameter updates, which requires a large number of circuit executions. Specifically, the parameter shift rule demands 2 circuit executions per parameter. As the number of qubits or the depth of the ansatz increases, the number of parameters grows, resulting in a significant resource overhead. To address this, we decided to reduce the number of circuit executions by decreasing the number of parameters, which would ultimately reduce the overall quantum computer resource usage. For achieving this, we didn't actually remove parameters from the ansatz. Instead, we skipped the 2 circuit executions per parameter required by the parameter shift rule during updates. We named this approach parameter freezing. In this context, the parameters that require 2 circuit executions in the parameter shift rule are called active parameters. During the Varkite iterations, we reduce the number of active parameters at intermediate steps. The frozen parameters remain unchanged at their current values. Our goal, as shown in the graph on the slide, is to converge to the ideal ground state energy while reducing the number of active parameters and consequently the total number of circuit executions. While working on parameter freezing in Varkite, we encountered several challenges. First, we observed that the algorithm sometimes failed to converge to the ideal ground state energy, instead converging to incorrect values. Additionally, in the early stages, the number of active parameters often decreased too rapidly, which also led to poor convergence. To address these issues, we implemented detailed mechanisms to prevent rapid freezing in the early stages and ensure proper convergence to the ideal ground state energy. Now I'll introduce the freezing mechanism. First, a parameter zeta is frozen if its average change within a specified window size is below epsilon zeta. Second, a parameter is frozen if the L2 norm of its corresponding column in the G matrix is below epsilon G. The magnitude of the column vectors in the G matrix comprehensively reflects the impact of a parameter zeta on the expectation value of the overall Hamiltonian. Since G directly captures the relationship with the observables, it provides a more physically meaningful criterion for freezing compared to simply using the magnitude of parameter changes. Freezing occurs only if both conditions are met. For the window size, we initially set it to a large value to prevent rapid freezing, and it exponentially decreases to a final window size over a specified number of steps. In our experiments, We used an initial window size of 20, a final window size of 10, and a decrease step of 50. Both epsilon zeta and epsilon g were set to 0.001. Additionally, to avoid excessive freezing, we limited the number of parameters frozen per step to 10% of the current active parameters and ensure that at least 2 active parameters remain at all times. In the following slides, we will present the results of parameter freezing across various problem graphs, qubit sizes, and discuss the impact of different hyperparameters. We tested various graph types, qubit sizes in max-cut problem, and hyperparameter settings to understand the impact of parameter freezing. Ansat's construction is detailed in this slide. First, we conducted experiments on an 8-qubit tree graph by varying the epsilon values. We observed that there was no significant change in the total circuit execution decrease rate across different epsilon values. Based on this, we decided to set the epsilon value to a small value of 0.001 for subsequent experiments. In this table, there are total number of circuit executions and the final Hamiltonian energy achieved after optimization. Closer values of those Hamiltonian energy to the ideal energy indicate better convergence. Total circuit decrease rate is a percentage decrease in total circuit executions due to parameter freezing. We experimented with the initial window size, final window size, and decrease steps as previously mentioned. We found that parameter freezing typically occurred after 50 steps, and the window size settings were deemed sufficient. Therefore, we continued using the same settings for subsequent experiments. We then conducted experiments by varying the qubit size on a tree graph. We observed that as the qubit size increases, the total circuit decrease rate decreases. But for 4 qubits, there are only 3 parameters, meaning only 1 parameter can be frozen, so the decrease rate is not significant. These graphs show the window size and the number of active parameters per step for each qubit size. While the amount of decrease in active parameters is similar across qubit sizes, the total circuit decrease rate is lower for larger qubit sizes due to the higher number of parameters. Additionally, this graph shows the L2 norm of the G matrix columns for each parameter across steps. It suggests that as the qubit size increases, the Hilbert space grows, making parameter convergence more challenging. Next, we fix the qubit size on a tree graph and increase the number of layers to increase the number of parameters. For 4 qubits, the decrease rate remains similar because the number of parameters that can be frozen is limited. However, for 8 qubits, we observe that the total circuit decrease rate decreases as the number of layers increases. These graphs show the window size and active parameter count per step for each layer. Similar to the qubit size experiment, the amount of decrease in active parameters is not significantly different, but the total circuit decrease rate is lower for more layers due to the higher number of parameters. Below graph show the L2 norm of the G matrix columns for each parameter. Unlike the case of increasing qubit size, which enlarges the Hilbert space, increasing the number of layers doesn't lead to less stable parameter convergence. We also experimented with different graph types, including tree, path, star, 3 regular, and complete graphs. We found that the total circuit execution decrease rate decreases for more complex graphs. However, for graphs with a large number of parameters, such as 3 regular and complete graphs, we observed issues with convergence or parameters failing to freeze. In these 3 regular and complete graphs, the norms failed to converge to small values. Specifically, for the 3 regular graph, the norms remain above epsilon g, which is 0.001, so no parameters were frozen. To address this issue, we tried increasing the epsilon value. When we increased epsilon g to 0.1 for the 3 regular graph, the total circuit decrease rate increased significantly to 24%, and we confirmed that the algorithm successfully converged to the ground state energy. This graph shows the increased epsilon value, and we can clearly see the parameters being frozen. Next, for the complete graph, which previously failed to converge properly, we increased the number of layers. This led to improved convergence. As shown in this graph, where the lines drop more quickly. However, even with this adjustment, no parameters were frozen. Finally, we fixed the number of layers at 3 for the complete graph and increased the max iterations to double and triple of the original value. Previously, all experiments used 100 iterations. With sufficient iterations, the complete graph successfully converged to the ideal ground state energy. This graph shows the norms remain above the epsilon value, similar to the 3 regular graph. We believe that increasing the epsilon value could enable parameter freezing in this case as well. And lastly, we experimented with increasing the complexity for Erdos-Renyi graph with 6 qubits. As we've seen in the previous experiment with different graph structures, higher graph complexity generally leads to a lower total circuit execution decrease rate. These graphs show the L2 norm of the G matrix columns, and we can see that the final converged to G norm values are larger for cases with higher complexity. When the complexity is lower, we observe that the graphs sometimes change dynamically, and let me briefly discuss those cases. For an edge probability of 0.2, several parameters, G norm values did not converge close to 0, and neither with nor without freezing did the system converge to the ideal ground state energy. And when the edge probability was 0.3, a few parameters failed to converge. Although the energy converged well, the total circuit decrease rate was relatively low. At an edge probability of 0.6, one parameter oscillated at the end of the iterations, and we can also observe a spike in the energy graph. To summarize our project, we applied parameter freezing to efficiently optimize work height, reducing the number of executed circuits, and demonstrated it across various environments. Increasing the number of layers or qubits led to more parameters and a reduced total circuit execution decrease rate, and a similar trend was observed when increasing graph complexity. In complex graphs, we believe that a larger Hilbert space and more interactions cause the G norm to maintain larger values, resulting in less freezing. However, we think that increasing the epsilon value in complex graphs could facilitate more effective parameter freezing. This is end of my slide, and thank you for your attention. And feel free to ask if you have any questions. Thank you.
Thank you. This is not a question, but I'd like to shout out Willie, who has given very precious and important feedback and direction to the Q player. Yeah, I'd like to shout out Willie. Yeah.
Yes, thank you. Yes, please.
Yeah, very nice presentation. I have a question about the different types of graphs you analyzed. It seems you looked at many different types, including regular graphs and complete graphs. For which class, like, okay, let me restate. Excuse me. Did you identify certain properties of the graph that would lead to having more or less parameters frozen? I'm thinking, for instance, the gap. Like if there's a gap between the ground state of the graph and the lowest eigenvalue and the next highest eigenvalue. Does that lead to a good or a bad behavior in terms of freezing?
From here, we just mentioned about the complexity of the graph, but I think the density of the graph can be a very important things to this parameter freezing.
Density meaning the number of edges.
Yeah, number of edges and also, yeah, that's right, number of edges.
There are some classes of graphs that have a very big gap. One example are so-called strongly regular graphs. I would be very curious about what happens to this freezing strategy when your input is a strongly regular graph. They only have 3 different eigenvalues. You can make them so that the gap is very big. And if I'm not mistaken, you can make them very sparse too. The number of edges doesn't need to grow quadratically. It can be significantly less, and you can have still a nice gap, I think, if you choose expanders. It would be very interesting to see in this.
Thank you.
What was the worst graph you've ever seen in terms of freezing, when no freezing happens? Was that the complete graph?
Yeah, that's right. Complete graph was the worst for the parameter freezing.
Okay, and which one was the best?
The best is
Star or something?
the for when we see from here, the tree graph is the best for the total circuit decrease rate. So the sufficient number that is not extremely large number of qubits and with the little edges I think that can be good for parameter freezing.
Then let me add, Martin. So Youngmin, so you said like the tree graph is overall the best structure for your parameter freezing, right?
From only for this line. Yeah.
And then what is the overall, like what is the structure that is best for overall?
We didn't find the best structure yet.
Just based on your experiments, like it doesn't, I mean, to be global, but like based on your experiments, what was the best structure overall?
I think the tree graph is the best because they have just the little edges and the connection is not very dense for the few places. So I think it's the best for parameter freezing.
Based on your experiments results.
Yeah.
Okay. Another question that's more on the programmatic side. It seems to me that the freezing procedure, it's sort of its own like twist on a hybrid workflow. It's a hybrid workflow, but you adaptively change your linear operation. Is that correct?
Oh,
So
yeah,
you will decide on the fly which ones to freeze based on some kind of maybe Fisher information or this norm of the G matrix. That's
yeah,
when it gets too small, or when changes get too small, then you freeze that parameter. It will never change again. Is that correct?
yeah, that's right.
But beforehand, you will not know.
Oh, yeah.
I see.
No. So basically, like it's determined on the fly.
Determine. In particular, it will be depend, I assume, depend on the initial distribution, how you start Varkite, right? It starts from a prior,
Mm-hmm. Mm-hmm.
which I assume you probably took uniform. Is that correct?
Uh, we, yeah, oh, yeah.
Hmm. Okay. Well, thank you very much. It's really interesting.
Oh, thank you.
I was curious if you saw any kind of a pattern in terms of which parameters were more likely to freeze. I'm not familiar enough with the way Varkite works so that I understand what the different theta i's are, but I'm assuming that the different theta i's come from different parts of the parameterization. And I was just curious if certain types of the thetas had a tendency to freeze more often than other ones.
Um, we're looking for all the parameters, but we actually not know the each parameters 그 each parameters. So I think uh for for these graphs there are so many parameters, but we don't know what parameter is where to place and what the parameters are working on something. So we're just seeing that parameters how they change for the steps.
Okay.
Danny, so let me ask again, like so Youngmin, what you said is there's no specific pattern you have found
Yeah, that's right.
from the parameters.
Interesting. Thank you.
Yes, thank you. Is there any more questions? And okay, it's up to here. And thank you for listening and thank you for your attention. Yes, thank you.
Very nice presentation. Thank you. And now we'll move to our last presentation today, the fourth one. This was a team that was mentored by Martin, and the name of the team is QuantumJoa. And this one focused on elliptic curve cryptography and its decryption code resource estimation.
Yes. So before we get into it, wanted to briefly introduce the team. The team is called Joa, which I think means I like it in Korean. And we had four very motivated and also very brave participants because this topic is extremely challenging. It's essentially cryptography. So as you all know, Shor's algorithm allows not only to factor integers, which can be used to break the RSA crypto system. It can also be used to compute discrete logarithms. And that is at the basis of a lot of cryptography that's being deployed, in particular to authenticate transactions on blockchains. It's very, very common to use elliptic curve D-logs. So the team looked into the discrete logarithm problem, the underlying mathematics. It's highly complex, a lot of modular arithmetic. They also looked into the business side, actually, what happens if these systems get broken. So I think we have here several members from the team, Jongbin Jo and Sekwon Choi. and the other members were Yeonsu Park and Yunming Lim. I don't know if the other two are here and who will start. I have no clue, but you have the floor now, Team Joa.
Okay, I start from now. Can you hear me?
Yes, and maybe I speak a little louder. It's a little bit faint.
Okay.
Yeah, it's good.
Okay, good morning. Maybe not for you, but in South Korea, it's good morning for everyone. And we are Team QuantumJoa. As like Martin Luther said, Joa means like, and we all like quantum mechanics and quantum stuff. So our team name is QuantumJoa. Our team is consisted of Hyungmin Lim, Seok Choi, Jangbin Jo, and Yeonsu Park, and they are all undergraduate students majoring in physics and electrical engineering and mechanical engineering. So let us begin our presentation. This is my tool. And first, I'm going to explain how discrete logarithm and ECC works in quantum way. So let's begin with the basic idea. In modular arithmetic, the discrete logarithm problem asks that given a base g and number h, we can find the integer x such that g to the power of x is congruent to h mod n. That is gx equals h mod n. And this is, for example, the right side. And let's say g equals 2 and n equals 11, and this is and h equals 9. So we can calculate the x by repeatedly calculating x equals 0, 1, 2, 3, and we could get the x value 6. And this problem is quite simple to define, but incredibly hard to reverse. Like, we need to calculate all the possible data of x. So especially for large numbers, and this is kind of ideal for cryptographic systems, I think. So we tried to find a way to calculate with quantum computing. As I mentioned earlier, classically, this problem is very hard. Like, no known classical algorithm can solve it efficiently for large inputs. But quantum algorithms could give a significant advantage. Like, we could prepare the quantum system in superposition for possible input values, so, and we compute GR mod n to quantum circuit that it performs modular exponentiation, and it's a key step because we need to resort to be entangled with the input exponent. And then we apply the inverse quantum Fourier transform. This is crucial step in many quantum algorithms, including Shor's algorithm. The QST essentially transforms our data from the time domain to the frequency domain, so it allows to extract predictably from the function. In our case, the period relates to hidden value x we are trying to find. After that, we measure the quantum state. The result of this measurement is a phase, which we denote as x over r. That is a fraction with x in the numerator and unknown period r in the denominator. This value is probabilistic, but if we repeat the algorithm enough times, we can get accurate information about x. And finally, we switch to classical computation. And we apply the continuous fraction expansion method to the phase value obtained for the measurement. And we implemented the full process of physics AR simulator, which was code from Navid Natalie's code conducted at 2022, and this is kind of the result. And this figure on the right shows the table of values, different x values that satisfy g over x equals h mod n. This result validate quantum algorithm and show how quantum computing can solve the discrete problem, which is otherwise very difficult classically. And the left side of this photo shows the theoretical basis from the Qustar. And let's move to electric curve cryptography, or ECC, the another system that uses the discrete log idea. But here, instead of working with numbers, we use point on elliptic curve. The elliptic curve is defined by x of squared x equals 3 squared x plus ax plus b. The solutions form a group structure, and we use this for secure cryptographic operations. The security depends on difficulty of elliptic curve discrete programming problem, or ECDLP. And oh yeah, this is elliptic curve discrete programming problem, and in the case of discrete programming, in the case of elliptic curve, we could define the point sum and point operators. Given a base point P and the point Q on the curve, we can find scalar K, such that Q equals KP. And this is ECDLP. And is and ECC has exponential complexity, and discrete Gordon problem has of exponential complexity. So we can think that using TCC could be very hard to solve. And from the previous researches, we found the Montgomery modular multiplication, which Zhongbin will show on the experimental data. So to explain the mathematical foundation, we explained that this Montgomery model explanation comes from GCD condition. We begin by choosing integers m and r such that GCD mr equals 1, and we define m prime as a modular inverse of modular r, just like m prime equals minus m, m minus over m over minus mod r. And we define T range condition, and let's define the intermutabilities, which was specified T goes between 0 and mr. And Montgomery reduction condition, we compute U equals T times M prime mod R, and we check that T plus M over R is an integer. And final output, which we compute the result of Montgomery multiplication, and T plus UM over R equals T R inverse mod M. This is the Montgomery form of T reduced to model M, but without doing the traditional division, which could be insufficient in quantum circuits. So if you look at the quantum circuits, the wires lab is X1, XY, Y1, X2, Y2, and represent quantum resistors. And this Montgomery multiplication, to be short, those Montgomery multiplication shows quantum speed up, and which makes kind of efficient. And we are going to implement this on quantum circuit, and we will show how it works. And Zhongbin Zhou will present this on the next slide.
Yes, hello everyone. I'm Jung-bin Jo, and I'll present the part of agreement description. So I'm trying to I'm trying to lift curve cryptography on quantum circuit using Qiskit. So I'm record this paper and yeah, let's start. This is Qiskit library. I use Doppler adder and integer comparator, and so it is I use main this three and yes. And I design modular arithmetic in quantum circuit using Qiskit, so it's important to uh, implementation of point addition. So first, I am trying to modular addition. So this left one is my code, and then middle one is a quantum circuit, and then last one is a result. Uh, Actually, first I'm trying to only unitary gate for quantum circuit, but it's difficult to for me. So I'm modifying my quantum circuit using non-unitary like this. This one is a not unitary gate, just a reset. So actually, it is not a quantum circuit, I think, but yes, it is work well, I think so. And then I'm trying to modular doubling. This is my code, and then second middle one is my quantum circuit using swap gate like this, and flapper adder is um not gate, as gate, yeah, like this, and measure. And then last right one is my result, and I think is good work. And I'm trying to modular multiplication. It is a combination of these two circuit or gate, control gate, so like this one. And then this is also work, but I don't check. I can check all of case, so I think it is a little problem. Maybe I think. And then this one is a modular square, and also is my curve, and this one is a quantum circuit. It is also use modular addition or modular doubling. And then this is my result, but it is also not sure. I'm not sure because uh, I think we use Kelly. I think Kelly or Angela Cuban not my circuit in my circuit not reset clean, so I have a little problem. And then this is a modular inversion and point addition, but I'm trying to this one, but it's uh too difficult for me. So yeah, I'm I'm not yet at this one. So yes, modular arithmetic are based on advanced mathematical techniques. So I'm trying to more study and design more efficient quantum circuit searching this. And then this is our GitHub code. So if you want, just check and then, yeah, like a feedback. Yes. Yeah,
Well,
thank
thank
you.
you.
Can you hear the video sound?
Is it only me? I cannot hear any voice from the video. Who's sharing now? I probably you should unmute yourself.
Yeah, I can't hear the voice.
I can't hear anything either.
When you share, you may try like sharing the audio at the same time. There's the option. So you can reshare the video. Just unshare your screen and click share. Is it Seok-won? I don't see his name though.
Okay, I'm trying with this file.
So when you share it, you should share your audio as well. There's the option, just checkbox, you can share your sharing.
Okay, I'm trying this one. Let's see if it's possible.
Wow. And also, I'm the team leader.
Okay, sounds good. Now I can hear.
Hello, everyone. I'm Hyungmin Lim from Team QuantumJoa, and also I'm the team leader. And today I'll talk about the elliptic curve cryptography and how it's impacted by quantum computing. So my part is introduction about the ECC. Let's start with basics. So I'm gonna talk about importance of ECC encryption. There are two main public key encryption. First one is RSA encryption, which is well known about the Shor algorithm. Second one is ECC encryption. So these are uses of ECC encryption. First one is transport layer security, which is about the SSL in web browsers. And second one is SQL shell, which is connect with SSL method connection with between the client and server. Third, fifth, the Tor anonymity network. This is well known about the dark web browser. And sixth, WhatsApp messaging app. This is using also ECC encryption. So these are many uses of ECC encryption, means the importance of the ECC encryption is very high. So I'm gonna talk about the security of the ECC encryption. Compared to traditional methods like RSA, ECC provides the same level of security with much smaller key sizes. For example, ECC 256 bits offers security compared to RSA 3072 bits, but with much less computational overhead. This is one reason it became so widely adopted. So this is the table about the elliptic security of elliptic curve and RSA. This is logarithm group means the RSA key encryption. But there's a catch. ECC relies on the hardness of the elliptic curve discrete logarithm problem, or ECDLP. So this means the security of the elliptic curve cryptography depends on the complexity of the ECDLP. Solving this classically is very difficult, but quantum computers changed the game. In 1997, Peter Shor introduced a quantum algorithm that can solve first integer factorization, and second is discrete logarithm problems in polynomial time. This means that even a powerful enough quantum computer, ECC becomes breakable. But we have to keep that in mind. This is FTQC algorithm, so this algorithm uses quantum Fourier transform, so we can do it in real hardware yet. So to break ECC 256-bit, first we need 2 qubits just to store the input about 512 qubits. Second, the quantum Fourier transform requires O to the n squared gate operations. And third, and to simulate elliptic curve operations, we need additional qubits for modular arithmetic and inversion. So, using optimizations like modular operation optimization and LDCP error code correction codes and parallel quantum operations, researchers have cut the logical qubit estimate from millions to around 6,000. That's a 99% reduction. This means breaking ECC 256 is no longer just theoretical, it's becoming visible on the horizon.
Hello, I'm Yoon Subak, the presenter of the presentation on the subject of cryptocurrency with the application of ECC announced earlier. For security and efficiency, most cryptocurrencies use a public key cryptography method based on elliptic curve cryptography. Bitcoin is a prime example of online cryptocurrency based on blockchain technology. It has characteristics that financial transactions can be freely conducted between individuals, person to person around the world. Now, what we are going to look at is how much is average transaction per day, and let's look at how much it's worth in US dollars. When referred in data such as blockchain site, Coinmetrics, Glassnode, the average amount of transactions per day is between 300,000 to 400,000 transactions on Bitcoin. It is also said that about $10 to billion is transferred per day based on total volume. Bitcoin protects transactions based on ECC 245 bits. Using a curve called SEC256K1, public and private keys are generated. The protocol is as follows. The role of ECC 245 bits in Bitcoin is that generates a public key through ECC calculation and hash it to generate a Bitcoin address. Here's a look at cryptocurrencies with weak randomness. If you make a crypto by choosing weak randomness, it is very likely to be stolen and attackers are actively target it. Weak randomness appears due to the way the underlying seed values are generated on a time basis. In addition, users choose phrases that are easy for ordinary people to remember by setting their own password and creating private keys, so they can be easily hacked and sometimes occur using a random number generation algorithm with security. In contrast, quantum random numbers have completely pure randomness. These days, commonly used random numbers or deterministic processes that are vulnerable to attack that substitute large numbers sequentially. Quantum random numbers can be viewed as complete random numbers by probability-dependent non-deterministic quantum measurements. Methods of creating quantum random numbers include the decay of radioactive elements or quantum optical method using singletons. This is an example of using a quantum random number chip. Recently, a Quantum 5 smartphone was launched in Samsung Galaxy with a quantum random number generator chip. The chip uses laser light, and it is unpredictable to measure the state of a few photons in multiple overlapping states, such as 0, 1, 2, 3. So the quantum random number generator built into the smartphone was used to collect random numbers during the probability process. Sharing quantum random numbers among communication parties will still traditionally use encryption as RSA or AES, but it is expected to be much strengthened by quantum cryptography or post-quantum cryptography. That's it for my presentation, and I will pass it on to the next presenter. Thank you for listening to my presentation.
Great. Thank you. Thanks, Team Joa. Any questions?
네, 질문 있으시면 해주시면 되겠습니다. Maybe don't. So we have one more team, but that team is their schedule is not matched, so they will upload their video. Martin, you already was told, right?
Yes. So they
Yeah.
record a very nice video. I don't know if you have time to play it, Junki.
I'm not sure if we received it or not. I think once we receive it, we will post it to YouTube on YouTube, and also we'll send it to you.
Okay, sounds great. Maybe I can just give verbally a very quick summary what the team did.
Yeah, sure, please.
This team also looked into the elliptic curve discrete logarithm problem. In contrast to the previous team, what they were focusing on was more the fault tolerance aspects. How do you actually implement this algorithm on a fault tolerant quantum computer? So what they did is, as a starting point, they looked at a paper from an individual from PsiQuantum. His name is Litinsky. He actually used the surface code to implement logical qubits. We heard in the presentation before, you need about 6,000 logical qubits. So kind of a surface code implementation of this. And then you can break it down to the physical level. So Litinsky has done it for two platforms, superconducting platform and ion traps, but it was based on the surface code, which is assuming a two-dimensional connectivity. So we were interested in the question of what happens if you have an ion trap-based quantum computer with more connectivity. So what was very nice, they looked at different classes of codes, the BB codes that the IBM has developed. There were some color codes they looked into, and a class called LP codes. So that latter class turned out to be the most interesting one. And they did, at the end of the day, they had resource estimates for how many physical qubits you need, and then also how much distillation you need to do and how long it would take in absolute times. And they believe they can bring down the overall resource footprints by an order of magnitude, which would be really spectacular. But what needs to happen is we need to test those and simulate the performance of the decoder. They haven't done that yet. That will be the icing on the cake. So, for instance, using a belief propagation decoder for the LP codes, one could actually do the end-to-end performance of the implementation of the elliptic curve Shor algorithm. And it looks like 400,000 physical qubits would be enough. They even think maybe one could do it with less, which would be very, very interesting and could even have security implications if everything checks out to be true. I think it was a great team, and I had a great pleasure working with both teams. The team from SKKU, there was an individual from SNU in that team, and the team from Yonsei University. Both were really great to work with.
Thank you. Thank you for the summary. So I think this was the last talk, and I really appreciate all the teams and the mentors for the attending this mentoring program. Thank you all, and thank you for the nice talks and it's your support. Thank you all. Thank you.
Hello everyone, it's Team Bank Thief, and I'm Singhan Bank. I'm sorry for the recorded presentation. Our research topic is resource estimation for ECDLP based on IonTrap. Quantum computing is a powerful tool, but it is challenging due to noise and scalability. So we need to quantum error correction and architecture study to overcome the challenges. In this study, we explored good QEC code for IonTrap and compare the performance of each architectures. The comparison is based on resource estimation for ECDLP. Elliptic curve cryptography is public key cryptography based on difficulty of inversion when we know only public key, and ECDLP is the inversion problem to find the private key K. If we use quantum computing, we can solve the ECDLP using Shor algorithm. And there are some papers about the resource estimation for ECDLP. We studied how many qubit and time are required for IonTrap-based ECDLP. IonTrap is leading quantum computing platform because it has long coherence time and high fidelity, and all-to-all connectivity. However, scaling is limited and operation speed is slow, so there are proposals to overcome the scaling issue. Photonic interconnection enables communications between separated modules using entangled photons. Shuttling enables the direct transportations of the data qubit. First, modular universal scalable IonTrap quantum computer, MusicQC. This architecture leverages an ion photon interface to enable remote entanglement distribution. Such distributed entanglement allows non-local quantum operations, which are performed through quantum teleportation or gate teleportation between distant modules. Next, quantum charge coupled device. Here the key mechanism is shuttling, which refers to the physical transportation of ion qubits across difference zone. This is achieved by dynamically shaping the electric potential using segmented electrodes. Through this process, data qubits are moved between various operation zones, enabling a form of dynamic all-to-all connectivity. Here, I introduce quantum error correction code what we used in this estimation. Hypergraph product code is one of the quantum low density parity check code, and it is made by two classical LDPC code. And lifted product code is multi-layer HGP code with permutation. Below the B42 is LP code we used. This code has significantly high encoding rate over the 0.1. When we do the syndrome extraction, we need only single shot with 8 entangling layers. To implement universal quantum computing, we need non-Clifford gate, and the magic state distillation is for fault tolerant non-Clifford gate. In this study, we used a 50-to-1 magic state distillation, and the encoding rate is around 0.005 with 10 to the minus 11 error rate. When we assumed no circuit error during magic state distillation. This is architecture part. For the music QC, the total physical qubit comprises data qubit, magic state distillation qubits, and EPR qubits. And the logical clock speed for 2 qubit gate is 9 milliseconds with QEC cycle. Finally, a fault-tolerant magic state generation rate is 2.8 milliseconds per factory. For the QCCD, the total physical qubit comprises data qubit and magic state distillation qubits. It doesn't require the EPR qubits unlike music QC. However, the operation time cost is proportional to square root of number of qubits because the shuttling time depends on shuttling distance, that is function of architecture scale. Therefore, the logical clock time is at least 13.5 milliseconds, and the magic state generation rate is 3.6 milliseconds per factory. Finally, we estimated the resource for ECDLP based on each architecture. The x-axis of the plots is number of magic state distillation factories, because the magic state distillation time cost is bottleneck when we have insufficient magic state distillation throughput. So the cross point between factory time cost and T-gate time is minimum of the space time cost. QCCD's cross point is 36 factories and music QC is 100. In conclusion, for the ECDLP 256-bit, music QC requires 7 million qubits and 47 hours runtime, and QCCD requires 1 million qubits and 166 hours runtime. Music QC has scale-independent time cost in contrast to QCCD, but QCCD do not need extra qubits for non-local operations. It is our result during the mentoring program, and it is only preliminary data. So our future work is developing the architecture and QC design, and next estimating resource requirements using realistic models. Thanks for the attention, and we appreciate the great mentoring from Martin. Thank you.